Here, Ramblers. This video covers Chapter 4.6 in our textbook and deals with rates and related rates. Now, we've talked all year about how the derivative represents the rate of change. But now we're going to be looking at some word problems where there's actually two changes going on and one is related to another. So in this video, I'm going to try and keep it a little bit short. So we'll start off looking at a real example, just something that, from around the house. And then we'll work on an actual word problem example so that you can see the different steps. I want you to make sure you get those steps in your notes. We'll make some videos later that get into more involved problems, but for tonight, let's just kind of see what related rates are and get the steps of how to solve the problem. So please pause often, take good notes, and thanks for watching.
Have you ever looked at how a washing machine works? It's actually kind of interesting. You put your wash and your soap into the washing machine. The washing machine fills up with water, and then it goes into the spin cycle. And during the spin cycle, all of that water gets sucked out of the machine, comes through a tube, and into this sink, this filthy sink. But as the water comes out, it's really important that the capacity of this sink be greater than the capacity of that washing machine. Otherwise, your sink's going to overflow. So what does this have to do with calculus? Well, maybe not the washing machine part, but the height of the water does. Let's take a look and watch how it happens. So the water's filling up the washing machine, and then it's going to hit the rinse cycle. All of a sudden, the water stops, and in a minute, it's going to start spinning. But we have to close the lid first because it won't spin with the lid open. So as you can see, we're on the spin cycle. Well, not yet. Let's move it ahead a little bit. Now it's on the spin cycle. And the water comes rushing out of this tube, and it starts to fill up the sink. Now watch what happens as the water starts coming in faster and faster. The hole going out can't move as fast as the amount of water coming in. So not surprisingly, the water in the sink begins to rise. So where does the calculus comes in? Well, it's curious to figure out how does the rate of the water level height change and what does it depend on? Well, it certainly depends upon the amount and the volume of water coming in, but it also depends on the amount of water that can fit out that little hole. And relating those different rates, the height of the water in the sink, the volume of water coming into the sink, and the volume of water leaving the sink are an example of what are called related rates. So let's see if we can't make any sense of these things.
For most of the year, when we've been taking the derivative, it's been for functions that are solved explicitly for y. So that when we took the derivative of both sides, we took dy dx was by itself, and we were left with 2x, and if you wanted to think about multiplying by the change of x as x was changing, you could, but who would do that? Because dx over dx is just 1. So we would be left with dy dx just equals 2x. And that's because we were taking the derivative with respect to x. Now, you may remember that we dealt with some problems where we couldn't solve explicitly for y. Something like xy equals, I don't know, x cubed y squared plus y. And using explicit differentiation didn't work, so we had to use something called implicit differentiation, which was really just an application of the chain rule. So differentiating this relationship would have looked something like this. So as we were finding the derivative, these terms dy dx would appear, and that is essentially what we would end up solving for to find the derivative. But the important thing I want you to recognize is that you can take the derivative, or you can find the rate of change in a variable
like we are with y, with respect to any other variable. It could be dx. I'm sorry, it could be with respect to x, as it most commonly is. But in these examples that we're coming up upon, in these related rates, it's typically going to be with respect to time. So you will see a lot of functions or a lot of problems where our answer is something like dv dt, where t is the time, or maybe you'll see dr dt, which is the change in the radius over the change in the time. And even though t does not appear anywhere in the problem that we're working with, the derivative is with respect to time. So that's going to come up in the next example. I'll be happy to answer any questions as they come up in class. So let's look at this example here. It says that a spherical snowball melts in such a way that at the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. Well, they want to know what rate is the volume of the ball of snow changing at that instant. So we're comparing two rates, the rate of change in the volume and the rate of change in the radius. And they should be related because we know that the formula for volume of a sphere involves the radius. So here's how I want you to set these problems up. We're always going to draw a diagram, and I always kind of like to keep it over here on the left side. And so this one's pretty simple. It's just going to be a sphere, and that's going to have to do for a sphere. And I like to label the different variables that I'm working with. In this case, I'm going to be working with the radius, r. Then over on the right side, I'd like to say the rate I want. And sometimes I just call it the want. And in this case, the rate I want is the change. What is the rate of the volume? So I want the delta volume as time is changing, because we're talking about an instant. So it's almost always in these problems going to be with respect to time. So the rate I want is dv dt. And then the other thing that we have to keep in mind is the rate I know. And the rate I know in this case is the radius. So we know that dr dt equals negative 3 centimeters per minute. Now, why do you think it's negative? Well, hopefully you recognize that since the radius is decreasing, that must be getting smaller, and that means a negative derivative. The last thing I like to write down is the equation. Any old equation will do that relates both the volume and the radius. Why those two? Because I know the radius is rate, and I want the rate of change of the volume. So I need an equation that has volume in it and radius. Well, obviously that's going to be the volume of a sphere, which you may remember from geometry, is 4/3 pi r cubed. So in order to solve this, I'm going to take the derivative. Now when I do that, I'll get dv dt, because that's the change, that's the derivative of volume with respect to time, is going to equal 4 pi r squared times dr dt, because once again we have to use the chain rule and multiply by the derivative of radius with respect to time. So now that I've taken the derivative, I can plug in the values that I know. Well, what do I know? Well, I want dv dt, so I'm not going to get that solved. But dv dt is going to equal 4 pi, and they tell me that the radius is 20 centimeters, and that the change in radius is 3 centimeters per minute. So I add all these, or I multiply these out, and I see that my dv dt is going to be negative 4,800 pi cubic centimeters per minute. That's a huge change due to just the negative 3 centimeters per minute change in the radius. But nevertheless,
It just shows you the effect of related rates. So you can kind of think back to the example with the washing machine, how the different rate of the volume coming in to the wash tub and the volume of water leaving is going to have an effect on the height of the water in the tub. Let's take a look at one more example for you to work on, and then we'll wrap things up. In the second example, we're told that a circular plate of metal is heated in an oven, and its radius increases at the rate of 0.01 centimeters per second, or a hundredth of a centimeter per second. At what rate is the plate area increasing when the radius is 50 centimeters? All right, Ramblers, I want you to set up this problem the way that I set up the last one, although I omitted something I'd like you to include. So the first thing I want you to do is sketch a little diagram in your notes, or there in your notepad or on your Notability. And then we want the rate we want. You have to make note of that. The rate we know. And then the thing I left out in the other example was the when. It's very important. And finally, the equation that relates the two variables, so that when we take the derivative, we will end up relating the two rates, hence the name related rates. Okay, pause the video, take a minute, go back to the problem, and pick out the rate you want, the rate you know, when, and the equation that relates the two variables. Okay, the diagram couldn't be simpler. It's just a circular metal plate, and we're working with a radius. Okay, well, what is the rate we want? Well, it tells us at what rate is the plate's area increasing. Okay, so that's going to be delta area, or dA dt. And the rate we know is told is the radius is changed. So that's going to be dr dt. And we know that that one equals 0.01 centimeters per second. And then the when is very important. That's when r equals 50 centimeters. Okay, what equation relates these? Well, clearly, the area, which is the rate we want, and the radius are related by the area of a circle. So area equals pi r squared. Now, it's very, very, very important that you don't plug in r at this point. You have to wait until we've taken the derivative. Otherwise, you've made r a constant, and there is no rate of change of a constant. So we never plug in until after differentiating. An important point. So I'm going to take the derivative, and so the derivative of area with respect to time is dA dt, and that's going to equal 2 pi r dr dt. And so there we have it. We have the rate we want, dA dt, and the rate we know, dr dt, in the same equation. We also have a spot for the radius, and at the instant that it's 50 centimeters, it has all the parts of the problem that we need. So let's plug in what we know and solve. So dA dt equals 2 times pi times r at this instant is 50. This is when we plug in. And then dr dt is 0.01. Now notice, unlike the other example, this is a positive 0.01 because the radius is increasing. Okay, so we're going to multiply all this out, and dA dt equals pi centimeters squared per second. Okay, Ramblers, let's wrap up with that. I hope you took good notes. Rewind if you need to pick up on anything, and thanks, of course, for watching.